Hi, my name is Arjun Ramani, and this is my video for the Davidson Fellowship Scholarship for 2017. In this video, I'll first talk about why my research project matters in the real world, so I'll give you some background information. Then I'll move on to how I got interested in this project and what I learned from it. Thirdly, I'll talk about how my project fits into the larger research context of the research that's already been done in this area, so I'll talk about the other literature in the field. And finally, I'll move on to the societal benefits and the impact in the real world of my project. So let's talk about why my project matters first. So my project is about generating random networks more quickly than what we can do right now. And so that's why it's titled Fast Sampling of Stochastic Kronecker Graphs. And so network science has grown in importance recently because of an explosion of big data in many different fields. A great example comes with Facebook, where the amount of users has grown exponentially in recent years. So what companies like Facebook and other network scientists want to do is they want to be able to identify the anomalistic properties or the weird patterns that occur in their networks more than you'd expect by random chance. And so a network is any place where you have objects or things that are connected to each other. So usually a network can be visually represented with a figure like this one right here. And so as you can see, you have many objects that are connected with each other. And we want to be able to identify the weird patterns within them. The problem is, this takes a lot of time. The way the network scientists identify the patterns is by comparing the real-world data set with a random network, or what would happen by random chance. The problem is it takes a lot of time to generate these random networks, because what you have to do is you have to put in probability values for every single pair of nodes or every single potential connection, and then flip a weighted coin for every single pair of nodes, and that takes a lot of time. So my project is a really big innovation in this field because it increases the efficiency for generating the random graph, which allows you to more quickly identify these anomalistic properties. And so that's kind of why my project matters. So now I'm going to move on to how I got interested in this project. So I've been doing competition math since a very young age. And so my favorite field in competition math has been counting and probability, because I think you can find really cool techniques and neat solutions to problems that you don't find in other fields. So in high school, I took a probability class at Purdue University, and so in this class, I learned a lot of really cool techniques that I wanted to be able to apply to more real-world problems and see if my problem-solving skills could actually do something that has not been done before, rather than just solving problems that people already knew the answers to. And so I contacted researchers at Purdue, and I was eventually able to find someone to work with on this area of computational math, specifically on Kronecker graphs, which is a type of random graph that I was analyzing and trying to create more efficiently, generate these graphs faster. And so that's kind of how I got into this project. And so in terms of what I learned from it, one thing that happened multiple times in this project was I came up to problems that I was unable to solve at first glance, and it took me many weeks to be able to actually come to a solution. So in my prior competition math experience, I'd always found solutions to my project problems fairly quickly. If I wasn't able to find a solution, then I would be able to look at a solution book and kind of come up with an answer. But with this type of math research, no one has done these problems before. So it took days and weeks on end at times to actually come up with answers. So one really good example of this comes with a portion of my algorithm that I developed called the backward mapping algorithm. So in this portion, basically once I generate the edges or the connections within my graphs, the connections that connect two people, I have to be able to figure out which two people that edge or that connection actually bridges. And so in order to do that, there's a lot of math involved, and I wasn't able to figure it out at first glance. So I was combing through the research papers in this field, and I eventually came across a figure of the fractal structure of a Kronecker graph, which you can see right here. So as you can see, these Kronecker graphs have patterns in them that I was able to exploit, specifically this fractal structure, that allows you to zoom in to various regions until you can finally identify where the edge is located and figure out which two nodes it's connecting. And so basically this idea of finding the fractal structure, which is something I found after weeks of doing research, finally pushed me over the hump in one of the key stages of my project. And it was a really important learning experience for me, and I got really, really excited and I had a lot of fun doing that. So that's kind of something I learned from this project, kind of developing my skills. So the next thing I want to talk about is where my project fits into the larger scope of the research that's already been done in this field. So there are kind of two places where this comes from. The first is a recent paper that was published in the journal IEEE in 2014. So basically, researchers in that paper, they discovered something about Kronecker graphs that's really cool. Specifically, that Kronecker graphs, these really, really big data sets, are actually composed of a bunch of common probability subregions called Erdo-Shreni subregions. So Erdo-Shreni subregions are basically these subgraphs that you can find in the larger Kronecker graph, and in each subregion, the probability of any two people or nodes being connected is the same. It's just a constant probability p, for we can say, to label a variable. And so the reason why this is important is you can decompose the very big Kronecker graph into a bunch of these smaller pockets, and it's very easy to solve the problem of generating the edges quickly in the small pockets. The hard part is putting everything back together. And so the previous paper did not have that efficient of a solution for putting things back together. So that's where my work comes in. I built upon the previous research and was able to find a way to assemble these pieces back together and kind of put the Erdo-Shreni pieces back together very quickly, like into the larger Kronecker graph, which built upon the previous research and increased the efficiency of this process. Another recent paper that my work builds upon is work done by Yuri Allen in the journal Nature, and he basically he developed the idea of the network motif. So a motif is a pattern of connectivity that appears in a network more than what would be expected by random chance. So when we're thinking about motifs, a really good example comes with the motif, the triangle in a social network graph. So a triangle is basically, if I'm friends with you and you're friends with a third person, and I'm also friends with the third person, then we have a triangle. The problem is, in most graphs, we don't have that many triangles. But in social networks, we have an overexpression of triangles. This makes sense because if I'm friends with you and you're friends with someone else, you're pretty likely to introduce me to that third person or for me to somehow get to know that third person. But if we're looking at a protein network, that's not going to happen at the same rate. Thus, in something like a social network, Allen was able to identify these motifs or patterns that appear more than what would be expected by random chance. And so he found these same patterns in other applications as well, like protein networks in biology and other fields as well. And so I build upon this because by more quickly creating random graphs, which is what my project does, then we can identify these motifs more efficiently, which is important because then we can figure out what's going wrong with various applications. For example, if we're in a protein network, it might malfunction and have some type of problem with its function, like an overexpression of some ligand that creates cancer cells. And so we would be able to identify those types of patterns of connectivity that lead to these problems with greater efficiency. And so that kind of leads me to the last part of my project that I'm going to explain in today's video, which is the societal impact, or how it really fits in the real world. And so let's go back to companies like Facebook and Netflix that have these really big networks. If they're trying to identify these patterns, increasing the efficiency of this random graph generation could save a lot of money for these companies. So we're helping the society by helping the economy, by creating more efficiency for companies that want to analyze big data and analyze big networks. Another important implication is what I was describing earlier about protein networks. If we want to find anomalies in these protein networks, then we can use this type of more efficient random graph generation to find these problems or patterns that lead to an overexpression of some harmful chemical or lead to more cell division, which could lead to cancer. And so that's really another example of the societal impact of my project. So when I take a step back and I look at my overall research experience, I know for sure that it's extremely fulfilling. I know that I'm doing something that could potentially have real world impact, and it's really cool to see all my years of competition math, interest and experience culminate in this more real world problem solving kind of atmosphere. And I also found it very fruitful to be able to solve problems that didn't just take minutes or hours or even days, but oftentimes took weeks on end. It was a lot more fruitful in experience to see a large body of work come to some kind of meaningful end and see my project advancing based on all the hours and time I had put in. And so as I can say for certain, I had a really, really good experience with this project, and I hope this video helped you understand my research experience a little bit better. Thank you.